if I change both x and little t by small amounts, how much will the temperature change?
Small amounts.
Presumably. Unless the behavior of this function here, t, is really kind of warped. You would expect to see small changes in this. Can I be more precise? Can I indicate?
Up or down.
Well, yeah, and you've got potential for conflict in terms of the up and down, but I want to be able to stick numbers on it, say. I want to be able to predict. The difference is that, with this, I've only got one variable to work with. That's, in this case, time. You give me small changes at time, I'm going to give you small changes in position. But here, I've got two variables, and what if they're both changing? What if one is increasing and the other is decreasing? How do those changes mesh? Small changes, because I can't do much with big changes because the function is likely not going to be constant in x or t. Okay, so there's a bunch of geometry that goes along with this, some nice pictures in the book, but let me just kind of throw out there what the answer. See, it always has to happen once. Don't ever touch this ball. Okay. So this is what we looked at with functions of one variable. What I would say here with my function of two variables. Is this. What we see is that if we have small changes in x and small changes in t, we multiply them by the corresponding rates of change in my function with respect to both x and t. Add together, it's going to give us this. It's just a slight generalization. Okay? The units here, temperature units. That's all we're measuring. Now, I'm saying small changes, they also could be treated as if they were errors, in a manufacturing process, say. There are things with the tangent plane which I'm not going to get a chance to get into, and I'm going to leave that with Tony. They don't give you any good problems on this. Dang it. Okay, well, let me just make up a little geometry one. Okay, So V is giving you volume of a cylinder that's of height h and radius r. Okay? If we measure h to within plus or minus, say, 0.1 millimeters, and we measure r to within plus or minus, say, 0.2 millimeters, what change in the volume would you expect?
Very small.
Very small, but we can be more precise. Now, I would have to get that level of precision, I would need to know what R and H are. Okay, so let's just say R is 5 millimeters and H is 50 milliliters. dV is going to be the partial of V with respect to R times the small change in R plus partial of V with respect to H times the small change in H. Notice that as far as units go, the units of dr here are going to cancel with the units of the dr here, leaving me with volume units. Here my H units also will cancel, leaving me with volume units. Volume plus volume gives me back volume units. So the differential of V is going to be 2 pi RH times dr plus, and then I want to differentiate with respect to H, so I'm going to have a pi r squared times dH. And the rest of this is simply plugging in numbers. So my dV would be 2 pi, my R, 5 millimeters, my H, 50 milliliters, times dr, this is an R here. Measure R to within plus or minus 0.2 millimeters, so plus or minus 0.2 millimeters, plus pi r squared, so that's 5 millimeters quantity squared, times my dH, so that's going to be plus or minus 0.1 millimeter. Notice millimeters cubed, that's a volume measurement, millimeters cubed here as well. And then from here you can simply compute. Okay? Now where this is going to take you is to the notion of a tangent plane. This gives you a way of measuring estimates on a function. So if you think about tangent lines to a curve, they give you an approximation to the curve near a point of tangency. And what that differential is doing is it's giving you an estimate as to how far off the tangent line approximates your function. If you look at a three-dimensional surface, say, it can be twisting and turning. You want to be able to say something about the behavior of the function at a point on that surface. Well, a tangent line isn't going to do it. So what I'm going to try and do is to generate out a tangent plane. And the idea is that if I make small changes in each of my variables, you add those up, it should be able to estimate small changes in f. That's going to give you the plane that you want. Okay, so that'll be covered also in that section. Okay, but I'll leave that one for Tony. In section 14.3, you should be freed up for the homework in section 14.3. I'll leave 14.4 homework for Tony. Okay? Okay, guys. Been nice knowing you.
Do you guys usually check your D12 page pretty regularly, or? Because I don't know if you use D12 pretty extensively. I use it pretty extensively also. So I think I've been granted access to your D12 page. So between today and Thursday, I'll try to send out, post a message there on the news wall about, things I want to post there and things I'll try to get up by Thursday night. My email address, if you need to contact me between now and Thursday, is TL Crossland.
Otherwise known as TLC.
TLC, yeah. At our Palisippi domain. So, and my office is in Alexander 212, just next door to Beth, actually. So, I'll go ahead and probably print off like a policy sheet for the second half of the semester with me. And so, I look forward to working with you. Just let me know if you have any questions.
Talk more. Man, I told him. I said,
Well,
what a great class.
you weren't weirded out with me sitting back there with
Pepper
you.
me.
Because I like to be as approachable as possible, so don't be too terribly weirded out. So
Where's Matthew going?
hopefully the transition will be smooth.
Which one?
It's Matthew, isn't it? The guy who's,
Yeah.
yeah.
That's why it was quiet.
Yeah, that's why. Anyway.
So,
Okay, guys.
There we go. Yeah.